So our next speaker is Siva Reddy, who has lots of affiliations, including Mila and McGill and IVADO, who is a co-sponsor of our semester this year. Siva's work has touched on many aspects of NLP, including topics like question answering and semantics. Recently, he's been pushing forward a lot of work in RL and agents, which I think is an exciting and relevant topic for the conversations we've been having. So I'm also very thankful of Siva. We switched to the slots, so he's giving the talk on short notice. We'll have the speaker in this slot originally speak later in the workshop. So thanks so much, Siva.
Thank you, sir. Hi, everyone. So this is my group's attempt to stay relevant in these exciting and hard times, in some sense. So you'll get to know what I'm talking about a bit later. So the goal of this talk is, it's very clear in this particular workshop, we are so excited about DeepSeek-R1 reasoning and reasoning chains and so on. And many of the talks touched upon reasoning chains themselves and what do these contain. And so we will dive deep into what does DeepSeek-R1 think of, right? And also we will find out if its efficiency, are these thoughts efficient or inefficient? And why are its thoughts inefficient? And let's try to improve. And the spoiler is that we will also be using credit assignment, and I would also touched upon progress rewards. It's very related to that. Okay, we are seeing a fundamental shift from large language models, and now we have large reasoning models. What it means is we reason first and then produce an answer, right? And then this reasoning is not a chain of thought prompting or anything like that. It's actually ingrained into the model. The model has incentives to think first and then reason, not just at the prompt level. And the biggest difference between chain of thought prompting and this reasoning ingrained models is that these models are fine making mistakes. They explore a solution, they might make a mistake, but that's fine. They might make many mistakes, they keep making mistakes, try to find the correct solution in the end. That's one of the biggest difference. And this also opens up a lot of potentials for inference time scaling, which we also saw some in the previous talks. Okay, so just for people also online who may not be very familiar with LLMs versus LRMs. So large language models can already do reasoning in the sense like it produces, to solve a problem, it produces many steps and then gets to the answer. The biggest difference, as I said, here is large reasoning models. They not only produce one solution, but they produce many alternative solutions. So that you see the thinking is very long. Here, if it is 10 steps, this will be 100 steps, 200 steps. And then in the end, again, it produces the final answer. Again, it produces 10 steps that we saw here. So in that sense, we have a much more sophisticated thoughts model, right? And for that reason, we are interested in this thing called Thoughtology, inspired from Bertology, where we are trying to see what these thoughts are. Like we want to systematically study what these thoughts are. My group worked really hard on creating this image. Many of the people who worked on this are here actually, so you can also touch them. Yeah, so we are trying to see what reasoning patterns it contains, inference time scaling. I will get into these aspects. Almost everything that has to do with thoughts, that's what we are going to delve into. As I said, this is my entire group's research effort just to stay relevant in these hard and exciting times. This is mainly led by Sarah and Arkil, who are also in the audience. We released this paper on Archive on Monday, but Archive blocked us. So we went ahead and did something else. It's too long for Archive probably. So these are the things that we are covering in this paper. You see scaling of thoughts, long context evaluation, faithfulness, safety evaluation, language and culture. psycholinguistics, visual reasoning, and so on. I won't be covering all of those. I'll be focusing mainly about the scaling of thoughts and things like that. Yeah. So what are these thoughts? If you actually look into these thoughts, they contain a consistent pattern. The consistent pattern is that they always start with a problem definition. Like you give an input, they go in detail what that input is. They just read out the input again. Oh, the person is asking me to solve x plus y. Just like really reading out the original input. That's the first step. And the next step is the Bloom step. This is the most important step where the model is trying to break the problem and get to the first solution. It gets to the first solution by this. You can think of this as some initial chain of thought. And once it gets the solution, these cycles start. We call these cycles called reconstruction cycles, and they always start with something like wait, alternatively, what if, so on, so on. And this is where the model spends most of the time. It keeps cycling and cycling and cycling, and then gets to the answer finally. Okay? Feel free to interrupt me at any point. I will give you an example what it means. Sorry, you can't read this, but I will read it for you. So this is a question about addition, some kind of addition, and you see this is where it repeats the input. It says the rope requires 2 bowls of blue fiber, half that much fiber. So blue fiber is one part. So it just repeats the input. That's the problem definition stage. And the next stage is the Bloom stage, where it does some planning, some chain of thought processing, and gets the first answer. So therefore, the total number of bowls would be 3 bowls in total. So it got the first answer. This is the Bloom step. And then we start the reconstruction step. And the reconstruction step usually focuses on the hard parts of the problem or the entire problem sometimes. In this particular case, it got fixated on one thing. And that one thing is half that much off. So in this particular problem, the model keeps repeatedly thinking about half that much. So that much refers to blue fiber, half that much white fiber. Half that much could mean so this is one cycle, reconstruction cycle. The second reconstruction cycle, again, it gets half that much. And in the first reconstruction cycle, it got an answer 3. So it got the same answer again. And it says that seems right. For some kind of verification also happened here. And the third cycle is also again the same, like it focuses again on half that much. It keeps repeatedly doing the same thing again and again and again, and gets an answer, most likely the same answer that it got in the first step. Okay. And as I said, like also not all reasoning cycles are equal in size. So the Bloom cycle, the first cycle where it gets the answer, that is the largest, that has the most number of tokens. You see, just focus on the thick blue line, and then we have all the reconstruction cycles, and you see there's also like ups and downs. So the reconstruction cycles, we are going down, the length of reconstruction cycle keeps decreasing, and suddenly you see a spike. And then keeps decreasing, you see a spike, and it gives, and overall, as the thought size increases, the reconstruction cycle size decreases in overall. But you see these spikes, right? And these spikes are what we call reblooms. They are kind of trying to find alternative solution. So if you take this reconstruction cycle, we see two main things happening in reconstruction cycle. One is the rebloom part, where it tries to come up with a different solution. This is the spike that you're seeing, right? And then the other part is rumination, where it gets fixated on something and repeatedly does the same thing again and again. And this cycle, sometimes it's even exactly repeating the same thing. So what we think is maybe R1 just discovered self-consistency, but with sequential sampling instead of doing it multiple times. Any questions on this so far? Yeah.
Is it literally a cycle has to say the word wait or alternatively? That's how you know?
Yeah, we came up with the annotation schema and then passed this annotation schema to GPT-4o. So GPT-4o, this is run on many thoughts. It's not like a few samples. It's the Bloom step is where we get the first answer. So we look for that one. The next steps are weight alternatively and all the possible things that you can think of.
I see. So GPT-4o is deciding when a cycle starts.
Yes. Yeah.
I have the issue with the word discovered. So the way this model was done is right in the prior, so already in the V3, you'll see some of these things that got distilled from some other data.
Yeah. Absolutely.
And then it just learned that it's a reasonable strategy and it started repeating it. But do we see like this number of cycles growing in some training on like if you took just the V3 compared to R1? Does it do less cycles, more? Like, is there anything?
There's a fundamental difference between V3 chain of thoughts and this chain of thoughts. The difference V3 there is it's trained on human chain of thoughts or even synthetic chain of thoughts, but those are mainly exploring one solution. Whereas R1 is trained on R10 chain of thoughts as well. And R10's chain of thoughts are in this fashion where it finds these aha moments. Right, these are called aha moments.
Can you see this quantitatively? Like the V3 does like one cycle or two, and this one does 20.
Oh, okay. Yeah, we did not compare that with V3, but that's a good point. Yes, yeah, we can. Yeah.
So, is it in the trace? Is it acknowledged that some things were previously said, or is it you that's observing the self-consistency, or is it the model acknowledging the self-consistency?
Yeah, we are observing that, like. So in this particular case, rumination, right? So fixing different people's seats. So this probably is coming again from one of these thing here. I don't see it here, but it's too long. Yeah, these are some things that we observed, and like we also have the rumination cycles clearly, which is mostly verbatim repeats of things. So you can see the model repeats exactly the same thing again and again. Even the solution is repeated.
But it doesn't acknowledge that it has done the same
thing?
It
does, no acknowledgement of that, yeah.
Do these cycles follow each other logically and then the final answer is dependent on the last cycle, or like that's traveling?
It's just as I said, like it's not incremental solution as far as we understand. It's again sampling the same solution again and again, or just it's self-consistency.
Does it take a majority vote approach that I tried 3 approach, now I will say 2 of them most common, so I will go with the most common answer?
Okay, so if you say here, okay, it's in the end it says I think I'm confident now, okay. And then it doesn't acknowledge that the many chain of thoughts produce the same answer. It says I think I'm confident now, so do 2 bolts. But it is very clear, right? All the reconstruction cycles produce 3. Like we have 5 reconstructions or 3 reconstruction cycles here. All of those are producing 3. Yeah.
Wait, to predict from the first cycle, how many more cycles the model will do?
That one I don't know. Like so, it depends on the problem. Maybe if I go into the more details, you will know some of these things. But you just see like the cycle length decreases. But some problems do not require this many cycles. They require fewer cycles. Is that your question?
Yeah, I'm just curious. Is the model flexibly adjusting how many iterations it needs to do?
It does. I will show you that. Yeah. I will move on. Sorry, I have so much other things, exciting things to talk about. So, yeah. So this is something the model also knows the complexity of the problem. So if you give problem 10 from AB, and then you ask repeatedly many times, so you see the model did not even use the other token. So we can go up to 18K. We did not budget force anything. We left the model to think as much as it want. And you see this problem does not require much, so it just stopped here. But some problems, like here, it started thinking in this bucket, some of these problems, right? And the pattern is consistent that it goes up with as the thoughts increase, and then goes down. And this is consistent across many problems. We tried this 40 thoughts per problem in AMI, and then we did some kind of normalization across all problems, and this is the curve that we observe. This is a normalized curve, so we can actually combine from all the problems. And as you see, as the thoughts go up, the accuracy goes, but then there is a sweet spot. And beyond that, it just goes down. So we don't, I think like it's very clear that inference time scaling is not that helpful for R1, at least. Okay? Yeah.
For this speaker, with each speaking problem is the same problem set, or they have different problems?
Different problems, but we normalize the based on, so if some problem usually starts with 1,000 tokens and ends with 10,000 tokens, we normalize that. And some problems might start with 100 tokens and then maybe 500 tokens. So it's normalized across all the problems. Yeah.
So in the answer to this problem, does it correct the answer correct at one of the changes, and then if successively because of wrong thoughts it gets it wrong?
Oh, we'll get into that. Yeah. Yes. Sure. And yeah, like so, if you think in terms of cost effectiveness or cost benefit trade-off, right? You might wonder, should I use more budget or should I use less budget? And it's very clear you should use less budget. Most often you should use less budget, because as you increase the budget, you don't see big trade-off. And after a certain point, it goes down, as I said. But at least for the parts where it increases, yeah, the first few tokens are really important. You get a big boost in it, and the next few tokens also you get very big boost. But after that, you don't get big boost. So it's doesn't matter if you increase. So here is something where we forced. So if the model has to produce 1,000 tokens, if we say 500, we just chop it off there.
You interrupted?
You interrupt it, yes, yeah.
Yes, so my question is related to that. When you say like the number of tokens grow, exceeds a certain threshold, the accuracy goes down. If you do early sorting, if you do some budget forcing at some point, would you get a good accuracy?
Yeah, so this is like let's take this problem, right? So if this problem requires 200 tokens, then so if it requires the 400 tokens, and if you just budget force it at 200 tokens, you probably won't get good accuracy.
Yeah,
or maybe
at this point, yeah. Sorry, so this different points are different traits.
Different traits, yes.
So in the last slides, there's a curve where you have, yeah. So here, if you stop earlier, so like when you generate the point at 0.6, if you stop earlier, would the accuracy be as if you are in the same point, or will you match the best accuracy?
It depends on the problem again. So if the problem is a simple problem, it is fine to stop early. But if it is a complicated problem, you do need, we saw, if you see here, there is a sweet spot for problems, right? And so the same problem, if you take, what is this, AMI 8th problem, and many times if you are sampling only solutions of length 8K, or if you're budget forcing up to 8K, the accuracy drops here.
I was talking like
maybe we could take offline, yeah, sorry about that. I have many slides, so at least like I thought some things are interesting for folks. This is also what we saw in the talk earlier by Alex. Yeah, correct solutions usually have shorter thought lengths. So this is observed consistently across data sets. Yeah, this is also what we also, Alex is not here. He said he would be here at 3. We cited his tweet, so tweeting is good. Okay. And no matter what we try, like you can't control the budget. So this we tried it in the prompt. Like we tried many ways to prompt the model. You cannot think more than this number of tokens. We will kill you, or whatever you do. Like it does not obey your command. It just like ignores that part and just does what it does. Yeah.
I mean, you would have to train it using examples like positive and negative. The
Right.
This is 16,000 and this is 8,000.
That's true. So we have to change the reward. Right now the reward, I will go to a bit towards the end, like the reward is just the formatting reward and the answer correctness reward, but there is no reward for length.
Okay, so that's it.
That explains. In even the paper, we even did a preliminary experiment where if we start having length rewards, what will happen? The model collapses if you're not careful. So if you say you cannot think more than this number of tokens, the model always thinks only in 100 tokens or 200 tokens. So we have plots for this. But then if you say you can think 100 less or more than this budget, then it kind of, if we design our reward such that it is plus or minus 100, but it has to go to that budget, it actually does obey the constraint. Yeah.
I'm familiar with the data set itself, so the questions are very normalized in any way in terms of their complexity, how many words in a question, and the model, like, is there a degree of difficulty? Is the model looking at the problem based on how many words in the problem, trying to budget the number of tokens to think about? Or is it
Yeah, like
normalized?
The model has some latent understanding of problem difficulty in some sense.
I could like ask a question in like 1 line or 20 lines, and
If you want to keep on going, just don't call people. Just push forward.
Yes. We'll take some of these questions offline. Yeah, we wrote 150 pages paper for this reason. Okay. Yeah. And then you might also wonder faithfulness to given context. Sibon Min, who was supposed to be here in the afternoon. So I mean, she wrote this great paper with Luke actually. That like in context learning examples, if you have some, if you mislead the example, give a negative sentiment, but then say the label is positive, right? Or just try to mislead the model. LLMs just ignore that stuff, and they will rely on parametric knowledge in context learning. And in this particular case, we have question answering tasks where we're trying to mislead the model, like Arctic Circle in Norway, where can you enter Arctic Circle in Norway? And we are saying Arctic Circle crosses Norway at Oslo. Oslo is the southern part of Norway, but this is incorrect. And the model reasons about it. Yeah, this is contradictory to my knowledge. But the user is insisting that I should use the given input. So it actually goes and sticks to that. Like it's very faithful to your input text, except for the length part. It doesn't know what to do with that, but for everything else, it does obey your inputs. Yeah. Okay. And then we thought like, what is OOD evaluation? Like, can we go out of distribution and evaluate this model? Almost all task theses are in distribution. They're trained on everything. So my student Benno, he came up with this creative idea. Why can't I do visual reasoning with these models, and let me try to draw dogs, cats, all kinds of compositional reasonings. So just like even for a simple prompt like draw a dog. So the model explores one solution, like it thinks, okay, this is how a dog looks like, and then it says, I will try to draw another dog here, and then it says, okay, I understood what a dog is, and now I know what the dog is, and it draws a completely different dog. So it's in out of distribution setting, it's not faithful to its thought. So this is one thing that we observed. Also, if you give a hard visual problem like some kind of text games, the model starts thinking in math and code. This is what the model is used to, so it doesn't even think in ASCIIs. Okay, yeah. So this is the reward that DeepSeek-R1 has. It has a format reward. The format reward is did it produce think tokens? Did it close the think token? Did it produce answer token? Did it close the answer token? That's the format reward. Very simple format reward. And then the correctness. That's it. So the model is able to discover. I mean, this is again a big word. Like as Lucas pointed, this could also be in the training data. But the model discovered the sequential self-consistency. What it did is that, and then it also discovered that it has to pay more importance to user input rather than the parametric knowledge. This is a big step, I would say, in some sense, because it is able to reason about someone. What it failed is it doesn't have this process monitoring. Sanjeev was also mentioning about in his talk, like this process monitoring is some of the metacognition is very important, and This model doesn't have that yet. And then it's also not faithful to its thoughts. In OOD settings, in distribution settings, yes, it is faithful, I think. Yeah.
So, OOD, you mean like that dog thing?
Yes.
But I mean, a transformer really can't reason very well visually. I mean, because to know what's the next, what's the I next to this, it has to count.
Yeah,
It's not
right.
an easy thing. So like that, those ASCII figures will generally be difficult.
It will be difficult. Okay. Even if we throw a lot of those, you think?
No, with enough data, anything.
With enough data, yeah. Okay. Right. Yeah.
Like
Yeah. Yes. But it is a hard problem. But what the model says is, okay, I understood. But we thought it would use a dog from its context, but it produced a completely different dog. This is not just for the dog, but we also saw this for anything else. We tried composition.
But I think in general.
Transformers,
like it's raster order, right?
Right. Yeah. So it is very hard. Yeah. Right. Thanks. Okay. So I did not talk about so many things. There are also some controversial things. You could go check it out. We did not talk about that. So what I want to focus here on is that these reasoning cycles are predominantly ruminants or infinite monkeys, as we saw in the previous talk. Yeah. So it seems like the model has essentially figured out sequential self-consistency, and this is also Denny was also on the first day. He was betting on self-consistency. This is one of the important things, and it seems the model essentially figured that out in some sense. Okay. Yeah. So it's not only self-consistency, but probably it's also inefficient self-consistency. So this is because we saw the ruminant cycles. They are complete repeats, like sometimes verbatim repeats of the same thing again and again. So it is sequential self-consistency, but an inefficient one. Maybe if you take other chain of thought models, like the kind of data that R1 is trained on, and then if you just do self-consistency, you probably will get better results than going through this entire route. So why is this happening? Maybe this is happening because you're getting reward only at the end, right? This is the actual algorithm that is behind the DeepSeek-R1, which we will also get into. And maybe what we need is stepwise credit assignment. We also saw in our talk, like there is a reward for progress, and that is credit assignment. We'll get into these things. Yeah. So this is a paper on arXiv, actually end of 2024, before DeepSeek came out. But these ideas are very relevant in the context of DeepSeek. I will let you know why this is the case. This is a work with my student Amir Hussain and Aaron Corwell's student Mila. Okay. So what do we want in reasoning, right? So we are given some problems, we are given answers, we are not given the reasoning chain. We want the model to figure out this reasoning chain. Right? And what we want is that the model, like there are many steps the model can produce, but what we want the model to produce are important steps. That's what we want, essentially. Important steps that could lead to an answer. That's exactly what we want. So identifying impact of each step, it's called credit assignment in reinforcement learning. I have been learning a lot about reinforcement learning, and this presentation does not require any knowledge of reinforcement learning because I had to rewire my brain to think about these problems. Okay, so many of you are already familiar with supervised learning, right? The supervised learning is just you're given some x and you're given also y. You're trying to maximize the probability of producing y, and then you take your gradients that increases this probability. This is the gradient descent equation for you. Yeah. So we want to maximize the expected probability of this thing, and for that, this is the gradient that would maximize that probability. Okay. But in the case of reasoning, the steps are not given. We know the target y, but the intermediate steps are not given. And we want the model to discover steps that are important. We want to push the model towards important steps. That's what we are doing. So what reinforcement learning does is you can call this reward, you can call this whatever. So because we are focusing at the step level, let's call this advantage. And if some step is important, that means the model, that particular step has certain Ys, and we want to retain those Ys. But if a step is not important, we want the model to not produce those Ys anymore. So this advantage here, if this advantage is positive, what we are saying is increase that likelihood of that step. So if it is an important step, we want that probability to be high. If it is not so important, the advantage is negative. That means decrease the log likelihood of that step. So that's if you think of this problem at stepwise. Is this clear? Okay. All right. So let's look at what DeepSeek did. So DeepSeek uses this algorithm called the GRPO, and it gets a reward at the end. Okay. So the model is taking many actions. So it took many actions, and then these are the gradients for each of those actions. You're computing the gradients, right? This is this part of the equation. So these are the gradients, and then you have to compute advantage of each step. But we don't know the advantage of each step. We are waiting for the reward at the end, right? And GRPO assumes the advantage of each step is the same. So it doesn't matter if it gets +1 in the end. Every step is important. Okay. So what you're saying is just increase the log likelihood of producing these actions again. Those actions will produce some Ys. We are just maximizing the probability of producing those Ys. Okay, so if you wonder what that equation advantage here is, for every step it's the same. It's the reward that it gets in the end. It's either 1 or 0 reward. And then there's also mean. Is this problem a hard problem or easy problem? So easy problems probably will get rewards of 1 always. So in some sense, you don't want to take it too seriously. But if it is a hard problem, that this is some kind of indication of hardness, or because you're sampling multiple solutions. So it samples 3 solutions for each, and gets the rewards for those 3 solutions, and then incorporates that into the final reward. Okay. The same thing for when it does something incorrect. It just pushes everything down. Every step, if it does a mistake, no matter how important is each of these, will just push everything down. Is this part clear? Any questions? Okay. So this one, the biggest drawback is GRPO, all steps are equal. And my student Amir Hussain, he talked to DeepSeek folks, and from their conversation that they chose GRPO because it's the easiest thing to implement for them. And this is probably why we are seeing a lot of rumination. Yeah.
What do you mean by step?
The steps, I mean, like if you break it by sentence level. So that I'm calling that step. Or if you can think of this also at word level, each word is a step.
Equally, just means there's no reward based on steps. That's what.
There's no reward, yeah. Yeah, exactly. So, yeah, there is an equal reward for every step.
Not the
equal reward. So there's a gradient for each step. That gradient can be less or more. So it depends on the action itself. But then the reward for each step is the same.
Oh, that's what
yeah.
There's only an end reward. It's the advantages you're talking about.
Yeah. Okay. Yeah. So this is probably why the model discovered, okay, it's not hurting me to have more number of steps. Let me have a lot of steps that actually produces the same answer again and again, and maybe discover the.
I mean, this seems like a huge logical jump, because RL, okay, maybe with advantages it is more data efficient, but in expectation, if you have enough data, you don't need partial advantages in RL. It will converge to the same thing, whether you have them or not. So why would you think that this would affect it's a variance reduction technique, not a bias.
Right, yeah.
So why do you think this would affect qualitative results?
Why this particular, why we are seeing rumination?
Yeah, I mean, this conjecture would basically rely on the premise that adding a variance reduction technique affects the outcome of the RL process, which could be true if your data is very limited, but I don't think it's that limited.
I see. Maybe that on that, like because the PPO that we will show, it reduces variance and at step level, like because you get reward at step level, and we sample multiple things. I will get into that. Like this is where we will. This is like here, even if you're for each problem, right? We are just like this very naive thing that we are doing here. Even if the model explores different solutions, it's not getting much. It's we are taking just an average over all those and just subtracting it from the reward of the current solution. Okay. Yeah. We could also talk about this again once we introduce PPO and VinePPO. Okay, so it seems wrong to treat all steps equally. So let's go and try something else. Like this is where we will start relying on the value of a step. And this is where PPO comes into picture, which has for a very long time it relies on values of steps. So what PPO and also our variant VinePPO does is you have gradients for each step, but now you have different advantages for each step. And some steps here we don't want them. We want to reduce the probability of those steps, and for some steps we want to increase the probability. So we are also multiplying this with the gradient, right? So this behavior emerges. Right, yeah. So what is value of a state? So the value of a state is what reward would you get in the end if you are in that state and sampled tried many solutions. If you try many solutions, what would be the final reward that you would get? So let's say you have this problem here and it has multiple steps, and if you are at step 1, if you sample infinite solutions from this step, okay, and let's say 2 of them are correct. In this particular case, I'm sampling 3, for example. Out of these 3, 2 of them are correct. Okay, so then the value of this state is. So when I meant correct, like from this state, I'm sampling the entire chain. So you have to sample the entire chain until to the end. And we see this particular case, it's 2 by 3, right? And you have to sample many things like that. Yeah. Okay. So that's value of a state, and we want to define advantage. What is an advantage, right? We haven't defined advantage yet. So this is where we're defining advantage. Advantage of a state is when we take an action in that state. So advantage of a particular action and state pair is how much are we going to get a reward? Like did we reach the answer here? We probably may reach. So this value will be either 0 or 1. We probably reached. We probably did not reach by taking that action. And then this is the value of the state you land upon, VST plus 1, and this is the value of the previous state. So if you land upon a new state by taking some action, your advantage is how much difference in value would you get. So this is how we are defining advantage. Any questions on this one? So what this says is, if you land on a state which will likely give you the reward, just go on to that state. If you, that's what it is doing here. Yeah.
In our case, so states means tokens. I mean, the value of the next token minus the value of the previous token?
Yes. Yeah. We could do this at token level. We could also do this at sentence level.
No, but the states are the entire prefix from the beginning of the prompt up until 17, right? They're not just the individual.
Oh, yeah. So that would be the entire thing. Yes, that's right. Good point. Yeah, first you. Discount. Yeah. So here we not talk about those things here. There's also. I'm not an RL expert, but there are also, like, you also discount. You can also think about some of in the value functions. You can also think there are these gamma terms which account for discounts and so on. I don't know the full details of that.
Discount what? There's no per stage rewards to discount. There's only a terminal reward.
Yeah. So in determining the value of a state, you could also think about what will happen if you can also think about what will happen if I go to the next state. How much should I give the importance to the next state? And from there, if I go to that, so you're in some sense also discounting for the future. But yeah, like we don't need that to understand. Yeah, what is it?
Depends how you calculate the value function.
Yeah, right. Yeah, exactly.
There's nothing to discount. You're not summing over a sequence of rewards. There's only a terminal reward. So, anyway. Okay.
Yeah, so this is what PPO uses. So it estimates the values of each step and then uses that to compute advantages. So now you might be wondering, how does PPO compute the value of a state? Right. So this is what we had earlier, right? So this is the ideal reward. Like if you know what the ideal reward is, so you could train a neural network to predict that value of that state. And this is done differently for different algorithms. So if you take RLHF, you have preferences, and from preferences you kind of build reward models, and from reward models you can go and build your value networks. So essentially what this value network is doing is it's, if you have training data some form for this step, this is its value. If you have some training data of that form, you're training a neural network to predict the value of that. So this is what PPO does. It has a network there that predicts the value of it. So not only like if you're training an LLM using PPO, this is why people say you have to have two copies of it in some sense. So one is where you're updating your LLM, and the other is where you have your value network, which is almost the same copy of that. Okay. So you can train. Let's say you trained a neural network that predicts all the values. Okay. So now, how good is it, right? Our current neural networks, are they able to predict the values of each steps? Okay, how do value networks accurately perform then? And then the question is, if we improve this value estimation, and that means we are improving the credit assignment. From that we can compute advantage, and advantage means we are improving credit assignment. So to what extent that would improve LLM performance? Right? So our current answer is that PPO provides inaccurate estimates, and then this is where we are introducing VinePPO, which relies on Monte Carlo sampling, and that has better estimation, which will lead to a lot of improvements. I'll get into these details. So this is the experimental setup that we have. Again, math setup. We have math data sets. And the models that we use are DeepSeek math. And these are the baselines that we are comparing with GRPO And then PPO, we also have DPO methods, some of these the RL-free methods. Yeah. And for VinePPO, which is ours, I will also get into that in a while. So this is where you see current value networks. If you have a neural network to predict value of a step, and if you know what that value of it, so this is the ground truth value of a step, and this is a predicted value. And take any point, right? Take this point. So ground truth, we are saying the value of this step is 0.5, whereas the value network predicts it as 0.2 or 0.1. So there is no correlation whatsoever. It's not, the model cannot predict these values correctly. And what VinePPO does is very simple. For each step, instead of relying on value network, at this step, we just do rollouts, lot of rollouts, and then compute its value. So if you have more rollouts, which means you're going to getting closer and closer to the truth value. If you have fewer rollouts, yes, it may not be perfect. Okay. So we use 9 rollouts, and for every step, like we sample some steps from the current LLM, from the current policy itself, and from that we go and predict the values. We do rollouts and predict values of those steps. Yeah, this is how it looks. So let's say our LLM predicted, according to our current policy, we are going along this trajectory. For each of those steps, we do some sampling, around 9 samples or so, and then out of those 9 samples, how many of them got the correct answer? In this particular case, 3 samples, how many of them got the correct answer? Okay, and all you need is, so like you clearly see that even with the 9 rollouts, our value estimation is so much better than using a neural network. This also clearly shows, yeah.
But 9 rollouts at every step.
Yes, 9 rollouts at every step. Yeah, it is on overhead.
Quite a bit.
I'll also show some plots where if you think in terms of performance, the wall clock time that PPO takes to reach the same performance as us, we are more compute efficient, even though we are doing a lot of rollouts.
Oh, compared to PPO. Okay.
PPO, yeah. Yeah, it looks slow, but it is very efficient that it learns very fast using this procedure.
How do you calculate the ground truth?
Yeah.
Good point, yeah. So in this particular plot, we sampled 256. For each step, we sampled 256 trajectories. I mean, we could sample even more, but I think 256 is at some point we saw the value is not changing beyond. So even 200 samples and 300 samples, there is not much difference in value that we are predicting. So we thought that 256 is a good one. Question?
But then what's the 9?
So this is the method that we are using. So like this is a ground truth is 256. That's the one that we want. But with 9 rollouts, we are able to get good enough. Yeah, this is where we are. Like you could try VinePPO on any LLM, anything, you would see this trend that it's so much better.
GRPO has this parameter of number of rollouts per problem.
Yeah.
So
that is, but it doesn't use that efficiently.
So when you in the slide that you just showed, do you like 9 times 20 that? Because you should compare with GRPO that does as many rollouts as you do in your Monte Carlo.
Yeah. So should look more into the paper, but like this passed the reviewer, so we are very thorough. But
how many rollouts do you do for GRPO?
Is it 3 or 9?
No, because it should be. Yeah, it should be 9,000, right? And GRPO's performance improves with the number of rollouts. It's a line in log space. So like this number, it depends on the number of rollouts. It's a function.
Right. So you're saying we are doing stepwise rollouts here, and here you're saying we should just roll out as many, like if we maybe, yeah. I will check out how many rollouts we are doing. I don't want to give an answer right
I think
away.
the more important part is all of this is a function of this number of rollouts. So
Right, yeah.
you're comparing two functions. They may cross or
Right, yeah.
different slopes or stuff like that.
But the fundamental problem remains that GRPO is giving equal credit to all steps.
But I claim this is not a problem. Like, if you do the same kind of rollouts, GRPO will be better.
Okay. Would be interesting to test. My students are here, so
I ran it and it was better. So
it is.
It's an opposing result.
So you run GRPO against VinePPO?
Version of GRPO, yes, with a different K.
Against
I ran a
VinePPO?
value function, and the value function gave no improvement at all. And the Monte Carlo something gave no
The
improvement.
VinePPO advantage or some other advantage function?
Well, both Monte Carlo and value functions, they gave no improvement. And DeepSeek says in their paper they ran Monte Carlo and it gave no improvement. So, but I mean,
But
you know, a lot depends on implementation.
Yes.
So if it does, it's amazing. But
If you run Monte Carlo and you force the advantage function to be a fixed constant across the entire episodic trajectory, that's not the same thing as allowing it to vary. That's the point he's making.
to have a value function, it can be a model. It can be
Okay.
Carlo estimate.
This is great discussion, but we could also take.
But there's a lot of details in
So in this VinePPO, how does the advantage get incorporated?
Oh, the same as what we saw earlier equations. It's we are predicting values, right? So this equation that we have, yeah. So just, yeah. So
No, but in GRPO, for instance, they were doing this rescaling by standard deviation. We are not doing any of that.
no, none of that. Yes. Okay. Yeah. So we do some big improvements. That's one thing, and as this is another scaling axis that we found. This is a training time scaling in some sense. You increase the samples, it goes up and up. So even for one sample, it's in this particular case it's same, but here we see it's actually better already. Okay, so what probably we want to think here is that this credit assignment is an important thing. We are probably just scratching the surface of reasoning at this point, and the next big things will happen in the credit assignment if you start thinking about credit assignments. But yeah, like Lucas is also saying, all you just need is sampling the trajectories, and you probably maybe not, yeah. But I take that point, yeah.
There's a lot of details just to say how you split into steps, how you how you
Yeah.
baseline, how you
Right, yeah. Got
If
it.
it works, it's amazing, right? But it just needs more.
As far as I know, it works.
No, but we should rerun like many.
Right, yeah. Yes. Yeah, so as I said, like it provides a scaling access during training time, one thing. Yeah, on that part, like so Amir Hussain and Mila, they created Nano R1. My group has been working very hard for this moment. So they actually they created a tutorial, a big tutorial, and also Nano R1, which can just replicate R1 on your laptop in some sense. So you should check it out. They also released an excellent video on this. Yeah. So with that, I'm happy to take more questions. Yeah. Thanks.
What do you do on the laptop? So what model fits? I mean, this is Olama or something? Or?
So this one, they're using Quen.
A tiny Quen.
Yeah, for Nano, Quen 2 billion or something.
But just to wrap up that conversation, it is true that in the R1 paper, they have this section, and they roughly say this other stuff doesn't work.
Right, yeah.
Given that you've clearly read that paper extremely closely, and VinePPO is also, I think, one of the few results that have shown these things work. What do you think, what do you make of that section of the paper?
It's been a while, Shashal. I'll be honest on that. Yes.
But you're still bullish on Monte Carlo tree search as a.
Yeah. So I'm very bullish on this because we did very fair comparisons with GRPO on this. In this particular.
Okay.
And the code base is also popular.
Yeah.
And people are using it, and no complaints so far.
Totally agree. The other part of me is like, they're pretty awesome.
Yeah.
And they did seem to compare against it in their paper, right? And say that they didn't see a benefit, right? So balancing those two evidence, it's unclear, right?
Right.
But could it be a data regime that the VinePPO does better? But if you scale to 10,000, maybe 100,000 and more, because GRPO does better because in a way it's kind of like needs to learn some sort of a.
Maybe like as I said, like.
I guess did you compare as you scale the data for both models, how they behavior changes?
Yeah. We've been very fair. Like, I mean, these are not really large-scale scaling efforts that we did. We are just like for the VinePPO paper, we use 7 billion model. But for the Nano R1, we're just using Quen 2 billion. And yeah, like that's the maximum that we could do at this point.
I think we have time for any questions here.
Thanks. So I remember in the DeepSeek paper, they have a plot showing that more RL step leads to longer COT length.
Yeah.
And your talk seems to suggest that the longer COT length does not necessarily lead to a better accuracy. I find it kind of confusing to me. Is that because the longer COT is very rare, or like what's the explanation to?
This again, like from what we found in the analysis of DeepSeek-R1 thoughts, it just seemed to ruminate a lot on the same thing again and again. So even if you have, so the model is doing self-consistency in some sense, and if it just ruminates the same thing,
that hurts accuracy. You kind of suggest.
Well, that's a good point. Yeah, it's not clear why it hurts accuracy. Like if it ruminates, it's not entirely clear. Self-consistency, as you increase the samples, it should increase, but we are seeing that it does not.
I think maybe the distinction is that it definitely helps up to a point. I think what you're seeing is like these very long outliers.
Yeah, so is that because such a long tree, super long trees, it's very rare, so it's like it doesn't matter to me.
I don't think anyone knows. I mean, it's a big conversation, but both things can be true, right? On aggregate, getting longer to a point could help, right? Then some examples could be bad.
Yeah, it's not rare. So like there are cases where there are overly long chains of thoughts, and these are like these overly long chains of thoughts will most likely be wrong because the model has either gone into this whole tunnel of self-verification and then trying to correct itself even though it has reached the correct answer, and then it fails, or from the start like it went down the wrong rabbit hole and like it just never found the correct solution, and that is why like it keeps on going until it is confident, and it never gets confident. So like all of these long thoughts are inaccurate on aggregate. Yeah.
So regarding the VinePPO, did it reduce the the chain of thought and?
Good point. We actually found it actually decreases the length.
It decreases the length. Do you have the plot that you had in the beginning for you had at the very beginning you had like what was that? You had 4 phases and then
yeah.
Do you have the plot for?
No, as I said, like, this paper we wrote before DeepSeek. VinePPO was written before DeepSeek.
Okay.
It's just around the same time, I would say. Yeah. So,
okay. But we
can go and
have the same plot and see whether it really helps. Right?
And right. Yes. Yeah. That's a good point. Yeah. We can compare some of these change that we get from VinePPO and R1. Yeah. Right. Thank you.
Time for one more question, anyone? Okay. Well, thank the speaker.